Welcome students to the fourth lecture on the MOOC series of statistical inference. If you remember, in the last class I was talking about estimating P, where P is the proportion of items in a universe U, say having an attribute A. So, this was the problem that we have done towards the end of the last class, and what we have found that if universe is equal to x 1, x 2, x n, of which P proportion having A attribute, we take a sample x 1, x 2, x n. If f is the sample proportion of items with attribute A, then expected value of f is equal to P. This we have found out in the last class. Today, I start with that with a slightly more complicated problem. Suppose there are machines M 1 and M 2, both produce items with proportion of defectives is equal to P. So, M 1 produce items and M 2 produce items, they are all coming to the common pool, and the manufacturer makes packets of 100 items. So, items being produced by machine 1 and items being produced by machine 2 are coming to the common pool. From there, where the manufacturer is taking 100 items and make packets. He wants to know what is the distribution of defective items in a packet. Packet means packet of 100. Suppose we want to find out this distribution. The problem is we do not know how many items are there from machine 1 and how many from machine 2. Only thing that we know if m items are from machine M1 and n items are from M2, then m plus n is equal to 100. This much we know. So, we want to calculate probability number of defectives in a packet is equal to k. Let us note that the total number of defectives can be k in k plus 1 ways, 0 from M1 and k from M2, 1 from M1 and k minus 1 from M2 up to k from M1 and 0 from M2. So, the probability that there are k many defective items in a packet can be computed by adding these k plus 1 individual events, and some of them may have probability 0. So, let us see how to work out that. Therefore, if x denotes the number of defective items in a packet, then probability x is equal to k is number of ways of choosing 0 defectives from machine 1 into number of ways of choosing k defectives from machine 2 plus number of ways of choosing 1 defective out of m from machine 1 multiplied by number of ways of choosing k minus 1 defectives from machine 2 up to m c k p to the power k This we can write it as sigma x is equal to 0 to k m c x p to the power x q to the power m minus x multiplied by n c k minus x p to the power k minus x into q to the power n minus k plus x is equal to, now if we look at it, this comes out to be p to the power k, which we can take out of the summation. This comes out to be q to the power m plus n minus k. So, that is also independent of x. So, we can take it out of the summation, and then what we get, x is equal to 0 to k m c x into n c k minus x. So, that is the expression that we get. So, now we need to find out this term. What is summation over x from 0 to k m c x multiplied by n c k minus x? To do that, let us consider 1 plus x whole to the power m into 1 plus x whole to the power n. So, this term is 1 plus x whole to the power m plus n. Now, let us expand both of them binomially. Therefore, if we consider the power of x to the power 0 here, which is m c 0, and multiply it with the power of x to the power k here, that is n c k, plus m c 1 into power of x to the power k minus 1 here, which is n c k minus 1, and like that power of the coefficient of x to the power k multiplied by the coefficient of x to the power 0 here. So, that is what we are getting as m c k multiplied by n c 0. So, this is precisely the summation that we are talking about. If you look at it, it is m c 0 into n c k plus m c 1 into n c k minus 1 up to m c k into n c 0. So, this is the summation that we get, and what it is. So, this is coef of x to the power k in 1 plus x whole to the power m plus n. Therefore, m plus n c k is equal to m c 0 into n c k plus m c 1 into n c k minus 1 plus up to m c k into NC 0. Therefore, the final probability is equal to, so this was the term that we have obtained. Therefore, final of probability x is equal to k is equal to m plus n c k multiplied by p to the power k q to the power m plus n minus k. Since m plus n is constant equal to 100, we can write it as 100 c k p to the power k q to the power 100 minus k, and this is true for k is equal to 0, 1 up to 100. Therefore, what we get? The number of defectives in each packet of 100 follow binomial with 100 p. So, we get the distribution of the number of defectives in each packet. Thus, we observe the following. We may need to infer about the sum of two random variables, and we want to know its probability distribution. In particular, if x1 is a random variable which is binomial with parameters m and p, and x2 is a random variable which is binomial with n comma p, then we find that x1 plus x2 is binomial m plus n comma p. When x1 and x2 are independent. So, this is one result we have established. We can prove it in a slightly tricky way if we make use of moment generating function. We know that if x1 is binomial with n comma p, then mgf of x1 is equal to, if you remember in the first class I have given you the formula. It is q plus p e to the power t whole to the power n. Similarly, if x 2 follows binomial with m comma p, then mgf of x 2 at t is equal to q plus p e to the power t whole to the power m. Now, you must have seen two results in your probability class. So, you must have seen these two results in your probability class, that if x and y are independent, then moment generating function of x plus y t is equal to the product of their individual moment generating functions. And the second result is that moment generating function, if exists, then it is unique. There are distributions for which moment generating function may not exist, but if it exists, then it is unique. What does it mean? It means that if mgf of x t is equal to mgf of y t for all t, then x and y have same distribution. That is, if x and y are two random variables having the same moment generating function for all t, then they have the same distribution. By applying these two theorems, we can see that moment generating function of x 1 plus x 2 at t is equal to moment generating function of x 1 at t into mgf of x 2 at t, and when they are binomial, then we can write it as q plus p e to the power t whole to the power m multiplied by q plus p e to the power t whole to the power n is equal to q plus p e to the power t whole to the power m plus n, with respect to the problem that I was dealing with. And this is precisely the moment generating function of binomial m plus n p. So, from here also we can prove that if x 1, which is a binomial random variable telling you the number of defectives in a sample M from machine M 1, and x 2 is the number of defectives in a sample size n from machine M 2, then x 1 plus x 2 will have a distribution which is binomial M plus n p. So, the results that I have shown you earlier by explicit summation can also be proved using moment generating function. Subsequently, in many examples I may use these results directly. Now, let us examine the example What is that catch? That both M 1 and M 2 have the same proportion of defectives. If M 1 has P 1 proportion of defectives, and M 2 has P 2 proportion of defectives, then we cannot get such a closed form. Therefore, when we deal with summation of random variables, we will try to see cases so that we can get a closed form for the distribution of the summation of the random variables. Another point is independence. When we are collecting samples from two different machines, as we have done in the previous example, we know that they are going to be independent anyway. But suppose we are looking at sampling from a population. If the sampling is with replacement, then effectively each of the selection of items are independent. But if it is without replacement, Obviously, the selection made up to ith unit chosen will govern the probability of selection at the I plus 1th stage. This is very clear, because it is without replacement. Therefore, the items that I have chosen till the ith stage, then when I am selecting the I plus 1th element, obviously it will depend upon the items that I have selected so far. Therefore, they are not truly independent. But consider that the universe is very large. The probability of selection of a sample whether with replacement or without replacement are very close. So, for your benefit, I have calculated some of these probabilities. Consider n is equal to 100, and I am choosing 3 elements from the population. So, when n is equal to 100, under SRS WR, that is simple random sampling with replacement, the probability of a triplet is 1 by 100 into 1 by 100 into 1 by 100, which is equal to 0.000001. Under SRS WOR, this is going to be 1 by 100 into 1 by 99 into 1 by 98. This probability is going to be 0.00000103. So, if we look at their difference, we find that the difference is coming in the 7th and 8th places of decimals. Similarly, for n is equal to 50, we get SRS WR 0.000008. SRS WOR, it is going to be 0.000008.5. So, again the difference is coming at the 7th decimal place. If we make n even smaller, then what we are getting for SRS WR, this is 0.000037, and for SRS WOR, this is equal to 0.000041. So, even when the size of the population is as small as 30, we find that the probabilities are very, very close. They are differing only in the 5th decimal place. So, that tells us something. So, that tells us that if the population is even reasonably large, we may consider each sample to be taken from the population to be independent of the other samples to be taken. So, what is the advantage? The advantage is that we can use the independence of probability by multiplying the individual probabilities to obtain the probability of selection of a particular sample of size n. Another important point is that given a random variable x, we may like to obtain the distribution of a function of x. For example, x is a random variable with mean 0. Therefore, what is the variance of x? Is equal to expected value of x square. So, given the distribution of x, we are trying to find out the expectation of a function, namely square of the random variable. For discrete case, this may be simple. For example, consider x which takes values -2, -1, 0, 1 and 2 with probabilities 1/4, 1/4, 1/6, 1/6, 1/6. Then how is x square distributed? X square can take values only 3 possibilities 0, 1 and 4. Probability of 0 is x is equal to 0, therefore, it is 1 by 6. Probability x square is equal to 1, that we can get in two different ways. When x is minus 1, whose probability is 1 by 4, and x is plus 1, whose probability is 1 by 6. Therefore, probability x square is equal to 1 is 1 by 4 plus 1 by 6, which is equal to 5 by 12. Similarly, probability x square is equal to 4 will coming out to be 5 by 12. Therefore, from the distribution of x, we can get the distribution of x square to be 1 by 6, 5 by 12 for 1 and 5 by 12 for 4. But now suppose I ask you, given this distribution of x square, can you find the distribution of x? Then you see that you cannot, because this tells me that probability x is equal to minus 1 plus probability x is equal to plus 1, that sum is 5 by 12. But there is no way I know the decomposition of this into the two values, which are the respective probabilities of x is equal to minus 1 and x is equal to plus 1. The question is, why we cannot do it in this case, but we can do in some other case. Say for example, x takes values minus 4, minus 3, 0, 1, 2, and suppose their probabilities are 1 by 4, 1 by 4, 1 by 6, 1 by 6, 1 by 6, then x square can take values 0, 1, 4, 9 and 16 with probabilities 1 by 6, 1 by 6, 1 by 6, 1 by 4 and 1 by 4. In this case, I can get the probabilities of different values of x. This we can do because the mapping from x to the function y, where y is a function of x, is unique. Given x, I know the x square, and given x square, I know which value of x has produced this value for x square. Thus, when the mapping is unique, it helps us to compute the PDF of a function h x of the random variable x from the distribution of the original random variable, namely x. I appeal to the following theorem, which many of you must have seen. Let x be a continuous random variable with PDF f of x, and suppose f x is greater than 0, on an interval a b. Now, consider y is equal to h x, that is y is a function of x x is strictly monotonic. So, from x we are mapping it into a random variable y which is strictly monotonic. Assume h x is differentiable and hence continuous. For all x. Then PDF, the probability density function of y is equal to h of x, is given by g of y is equal to f of x multiplied by dx dy, the mod value of that expressed in terms of y. Now, why did we take strictly monotonic, whether increasing or decreasing? Suppose this is x and this is a strictly monotonic function of x, then given y, what is the probability that the random variable y is less than equal to a particular value y? So, that probability will come from the probability of x. So, that probability will be given by f of h inverse of y. The strict monotonicity allows us to make the inverse of y and to get the value of x, and therefore, we can apply the cumulative distribution function of x on that one. So, let me give a very quick proof of the above statement. So, we have taken an increasing function. Therefore, g of y, which is probability y less than equal to y, is same as probability h of x less than equal to y, and since it is strictly monotonic, we can get the inverse of y uniquely, and therefore, this is f at h inverse y. Therefore, what is the PDF of y? we get it by differentiating the cumulative distribution function. So, this is d dy of f of h inverse y, which is multiplied by d h inverse y dy, where x is equal to h inverse y. Therefore, we get it that g of y is equal to f of x, h inverse y is equal to x into dx dy, and this we express using y. If g is monotonically decreasing, then what will happen? G of y is equal to probability y less than equal to y is equal to probability h of x less than equal to y is equal to probability x greater than equal to h inverse y. This is because it is decreasing. Therefore, inequality will be reversed, is equal to 1 minus probability x less than equal to h inverse y is equal to 1 minus f at h inverse y. Therefore, d g y dy is equal to minus f at h inverse y, which is f into d h inverse y dy, and we know that if it is a decreasing function, then this derivative is going to be negative. Therefore, that multiplied by this minus sign will give you the modulus of the derivative, right. Or we can write it as f x into mod of dx dy. So, if x is monotonically increasing or monotonically decreasing, we can get the inverse. That is not the case. Say for example, h of x is like this, then given a y, I can get two different values of x, and we cannot take the inverse of y. In a similar way, if it is something like this, although it is increasing, but on this range the value is fixed, then also for these values of y we cannot actually get the inverse of the h function, and therefore, in these cases we have to apply some tricks to partition it into non-overlapping segments, and from there we will have to calculate the PDF of the function of x. With that, I stop here. In the next class, I will use this theorem and I will show a case of this type to show how we can obtain the distribution of some functions, particularly of normal variable. Okay. So, with that I stop here. See you in the next class. Thank you.